Then on larger here, just showing the identification of the bin detection. So first of all, here's bin A detection. And as you can see, it's showing the sequence onto the screen, so it's continuously refreshing there. And this is just a quick setup of the embed of where the light flashing is coming from and the overhead camera. And once again, here's bin B detection, same setup here with the camera, and here's just a screen capture of recording the red circles, blue or green circles, so that'll show up on the screen as well. And here's the sequence again. So the good thing is, because it's continuously refreshing, it should be accurate most of the time. Even if it gets it wrong once or twice, it should eventually get it. And finally, here's bin C detection, same setup again. It's using a Python code, so it can be easily integrated onto the Raspberry Pi, which I've done as well, but this is just on the computer just to show the whole setup. And once again, here's the sequence here. So as you can see, it's pretty accurate up to 0.5 meters away, and considering it's going to be attached on the robot, it should be fine for the task. To identify the recycling bins from different optically coded sensors, we used a camera-based detection system to pick up the different RGB colors. This was implemented using a Python code which detected the RGB colors using a webcam. The Python program uses OpenCV software to convert the RGB colors to the HSV color space. This in turn prints out the sequence to match the criteria, whether that's bin A, B or C. And this can detect sequences from any point, which means that it doesn't have to start from the beginning, it can pick up the bin from any point in the sequence. The level of autonomy for this is currently level 3 conditional automation, which means that it only requires human interaction to calibrate the program at the beginning, but can autonomously reset and pick up other bins by itself. The limitations currently is that it cannot pick up the LEDs further than 0.5 meters away, which would mean that the camera has to be attached pretty close to the ground in order to be more accurate. So the second clip here is just a rubbish collection and sorting demo, and it's the same format as the first clip but just a extended version, just to show how in the overall scenario of collecting and taking the rubbish, how it works. So currently it's only manual control because we didn't have time to integrate the autonomous features onto the arm. But as you can see that the extended gripper here is collecting any rubbish type, so over here it's a cardboard box, but it can be anything, a plastic bottle or what, or anything, and it would work fine because of the size of the extended gripper. And as you can see, because it has 6 servos on it, so it has 6 axes of movement, it can pretty much pick up anything and has full flexibility, so the robotic arm is useful in that feature. Once it's got the piece, it can just simply turn around. It can turn on the spot, so it's pretty maneuverable, the tri-track as well, and it will take its rubbish to its desired destination, so for this purpose of the demo, to the other side of the room. Now the plan was to integrate the capacitive sensor onto the surface face of the extended gripper, and what it would be is, once the capacitive sensor is integrated, when the extended gripper would pick up the object, so for example this cardboard box, it would be able to tell what type of object it is and then take it to its desired position. We didn't get time to integrate this, but that would have been the plan. And over here you can just see that the robot is just going back to its original place. Once again, this is only manual control using the Xbox controller, but the integration of the autonomous features could be implemented quite easily. To demonstrate the identification, collection and intelligent sorting of the rubbish into appropriate bins, we have two current solutions to that. One of them includes the TriTac robot, which includes the fully functioning robotic arm, and that is fully functioning using the Xbox controller manually, but also has functions built in depending on the different type of rubbish to autonomously deploy the arm to pick up that object. The second option is using a pick-up scoop mechanism for the Danny robot, which is currently not implemented yet due to 3D printing issues, but the plan is to have a scoop mechanism which provides a different solution and is part of our innovation. The level of autonomy is currently level 1 driver assistance due to not having full autonomous control of the robotic arm deployment, because the success rate would be likely low, which is why the most likely scenario would be manual intervention in case if that happens. As mentioned, the limitations is that the autonomous deployment of the robotic arm is quite low at the moment, so it would need some form of intervention, which would most likely be the Xbox controller.
Currently, the design of the bucket loader is finished on simulation software, but now we're waiting for it to be printed so we can test it. On the simulations, it was possible to see how the different parts and joints will interact together to see if the arm could ascend and descend. The idea behind this mechanism is to be able to prevent obstacles getting jammed underneath the Danny robot and also pick up rubbish or larger pieces of rubbish, such as a bottle or cans, and carry it to place close to the bins, so it can be separated into different types of rubbish thanks to a capacitive sensor located on the Lynx Motion AL5D arm.
The intelligent route finding capability on the beach is carried out using the Danny robot, which is connected to the eye in the sky. So the eye in the sky will basically look down and see where the robot is and where the piece of rubbish is, and then on a coordinate grid pass down to the Danny robot which coordinate the robot's in and which coordinate is the goal. And from that, the Danny robot, through LabVIEW, will use path planning VRs and the ultrasound sensor to plan a path towards the rubbish, and every half a meter it will stop and retrace its area so that it knows if there are any objects within its vicinity that it read wrong or incorrectly, and it will update the occupancy grid and then plan a path again. And this is what the robot will constantly do until it reaches the point of where it needs to be.
We have a bottle to test the rubbish detection, which will meet all of these mission phases. So what we're going to do now is we're going to go to the computer and we are going to demonstrate how the software works. So, right now I'm in the Detox Viva test client, which is just an example of the functions here. So here we've got the view of the arena here. We've already got the fact that it's detected that the bottle is here. And if we look down in the data view, we can see that it has detected that the bottle is there. We can also go ahead and show the grid, which is behind my camera here. But we can reload this with new settings, and as you can see, we have a grid.
Alright, so here's, without the sensor applied to anything, there's a setup. Applying the sensor, the light turns on, and the voltage is changed. Take it off, and then put it back on. Sweet. Take it off. Put it back on. This is the capacitive sensor readout VI. The sensor voltage is being read out through the MyRio into the VI and determined using logic what material is being read.
So to summarize and identify different types of rubbish, we have two options that are shown, and the first option, which was the high-eyes camera-based ORB algorithm, which uses an OpenCV algorithm. That worked successfully as it managed to identify all rubbish types, including the plastic bottle shown in the clip. The second option, which is part of our innovative solution, was the capacitive sensor. While we didn't manage to fully integrate it, the videos and testing did show that it does manage to identify object types, and we have a LabVIEW based GUI integration. The level of autonomy is level 2 partial automation because the capacitive sensor does require human interface with the GUI LabVIEW. The limitations are that the capacitive sensor needs objects which are 2mm thickness, and the level of accuracy isn't the highest with the sensor.
So you can see me standing here, it thinks I'm stood inside of it. Which will break it. And also, if it saw this gap in front of it, it would have thought.
Then we start making these sort of false claims.
Especially if you put a sound system, absolutely. For identifying and characterising different crab types and their routes, that capability is already put into the High-Eye software, what we call in the Eye in the Sky. It's just a much easier name to remember. So from current testing, we can identify them and classify them from up to 2 meters distance off the ground using the software. What we are doing is making a calibration program that will make that a bit more accurate, and we'll be able to get some accuracy data there soon. But aside from that, it does use a virtual grid to draw the lines for cab routes and recognize their positions. So effectively, and it will expose that information via web API. It uses JSON, which is, just a standard data exchange format for the web. And yeah, what the robots can do is they can connect to it, because the Raspberry Pi, obviously you can make a Python program that reads JSON for that. LabVIEW also has JSON capability, so it's pretty standard and it's built in. That's made using the Flask framework and Python. And because of that, the thing has level 4 high automation. There is a calibration program being written right now that will allow you to pretty much just get the crabs in the right position and kind of build up a database of different crabs, as well as the robots as well. We're going to add robots to it. And the intention is to have those kind of mapped to a control panel so you can see where they go. Obviously, the level of accuracy we can't measure right now, so that's coming. And it struggles to identify crabs beyond 2 meters, but that's probably an issue of the calibration, which obviously we'll sort out pretty soon. Hello, this is William from Team Detox, and today I am going to present to you HiEye. HiEye is an overview system. It's also something that can detect or waterline from data shown by the operators. It can track any moving objects or static objects such as rubbish or wildlife. And it can also kind of track their paths as well and output that data via a common data format, so that our other 2 subsystems, our robots, can navigate the beach using that data. So I will show you that right now. We'll hop back to the computer and I'll show you the whole setup, how it works, and yeah, just have it in that. So here is our setup for HiEye. As you can see here, we have the Raspberry Pi 4 with the webcam connected to it. The operating system that the Raspberry Pi is running is a specialized build root customized operating system. It's Linux based, and that has OpenTV and Flask on it. The reason why it's reduced is because there's not many good operating systems for the Raspberry Pi 4 apart from Raspbian, and plus it's just to reduce overhead for the entire system so this can work as fast as it can. But yeah. And next we have our webcam, which is on this pole right now. Obviously, due to the current situation, we can't have it as high up as we want it to, but this is a good example for what would have happened. And as you can see here, we have the 3 crab images, and we have a bottle to test the rubbish detection, which will meet all of these mission phases. So what we're going to do now is we're going to go to the computer and we are going to demonstrate how the software works. So right now I'm in the Detox HiEye test client, which is just an example of the functions here. So here we've got the view of the arena here. We've already got the fact that it's detected that the bottle is here. And if we look down in the data view, we can see that it has detected that the bottle is there. We can also go ahead and show the grid, which is behind my camera here. But we can reload this with new settings, and as you can see, we have a grid. We can show the paths also on that grid as well. So it might not show all the paths, but that's mainly because we haven't got any objects that have moved yet. So what we can do also is just show the object's paths. Data view here. As you can see, nothing has moved yet, but I could probably bring in a crab and it might be able to detect it. If not, that's not too much of an issue. Sometimes it doesn't work. I've had problems getting it to work in this specific environment, but it does work in others have tested it. So for actively avoiding interfering with the crabs, as I said back on identifying the crabs and the crab routes, that functionality pretty much should be built in, and it's really just an extension of, identifying the crabs and their routes. All it'll do is the robots will pretty much know where they are and know not to go into those squares effectively. They'll be blocked off and it'll know not to go into those things. And that data will update regularly, just so, it knows where the crabs are and it can, try and make decisions pretty quickly based on that. And also, if we can get the time, we'll also try and get it to kind of recognize the paths and kind of figure out where the crabs will go next. And as this functionality is pretty much concentrated on the high software as well as the robots themselves, this is a level 4 automation and only requires the calibration at the beginning. And of course the limitations are the data transfer rate. I have tried manually refreshing it and trying to see how fast the data updates. It does it at a reasonable speed, I'd say every millisecond or so, which shouldn't be too bad. Of course we've got to do further testing with the Pi just to see if it'll actually work, but I am pretty confident that it will.
This is the sound detection module for the overall beach cleaning system to detect the seagull in the area. So it's controlled by this seagull boolean. This is what's passed back to the operator so they know if the seagull is in the area. In the module it shows you the one seagull call that's being cross-correlated with to test whether or not the similarity is enough to justify a seagull in the area. The correlation graph is what's used to calculate the similarity between the recorded signal and the original signal, and the recorded graph shows you the sound that was recorded in the time domain with the amplitude across time. In the other panel it shows you the code that's used to calculate this. So all of them follow the same code is applied to the original seagull call. Is filtered so that only because the seagull has a threshold good frequency which is between 1-3 kilohertz. So a bandpass filter is applied and then it's passed as a cross correlator, and then from the cross correlation it then detects it uses a threshold to detect whether or not a seagull is in the area or not. So I'll show you this working now using the seagull sound that we were produced with. So if I press run and play the seagull sound, the seagull's playing in the back and I can still talk over it because it can filter out the noise of my voice and all. So now it's completed the recorded sound. This is a recorded sound that was heard, and this is the correlation graph which shows the similarities. And you see there's a few peaks in the middle of it, and these peaks are used to decide, since there's more than one peak, that peak will say, for example, that a seagull was in the area, and that's how it works. To detect other wildlife in the area and alert the operators, we're using the MyRadio combined with a microphone to listen to sound in the area, and if a seagull call is heard, it will flash a light to say that a seagull has been heard in that area by using cross-correlation techniques. So the current capability is that using the microphone at the moment, we can autonomously identify a seagull up to 4 meters away, but above 4 meters, beyond 4 meters away, it's hard to detect because it doesn't meet the threshold anymore because there's too much noise in the area. But from the cross correlation graph, you can see that there is a seagull call. So manually, you can identify that above 4 meters that the seagull is there. But we assume that if it's above 4 meters, if it's away from 4 meters, then the seagull is far enough away to not cause a threat to the robot, and therefore we ignore it.
Now, what we can do also is we can enable the waterline. And what this should do is it should show a waterline down here, and if we go back to our position view here, it should show us where our waterline is. So it says 2, that means waterline is at 2 at the top, and so 2x and 2y basically. So the robot should not be able to go past that coordinate grid point, because it will get this data view, it will know where it is in the grid, and it should not go past that point.
So to summarize identifying the waterline and actively avoiding or mitigating its incoming tide, we have successfully simulated a waterline using the HiEyes software. The level of autonomy is level 4 high automation, because the simulated waterline simply only needs to be passed on at the beginning. The limitations are that the simulation is not real time and is only a virtual implementation.
So what you can see here is the graphical user interface for our Detox speech clearing system. Here would contain a video stream from the HiEye, Eye in the Sky system, and over here would be a video stream connection to the grabbing robot on the grabbing arm. You'll find out more why in a bit. There's two modes. There's the automatic mode, where it's the autonomous system, where you can change that to be in manual mode, and that gives the user full control of the system and gets rid of the auto elements. So in automatic mode, the HiEye system has identified an object at these coordinates. We then have the option to send the grabbing robot or the scooping robot. So if we send the grab robot, it will tell us that it's moving to those coordinates, or we can choose to send the scoop robot. Then have the option to cancel the instruction if we no longer want to go pick up that object, and that will just get rid of anything that's there. We can also check the location of each robot if it's difficult to distinguish them on the screen. So we can see that the grabbing robot is at these coordinates, and then the scooping robot is at these coordinates, and that's just a simple click of the button. We've got our wildlife detection system here, and it's identified that there is wildlife near to the system, but it's 4 meters away. It's not quite close enough to be 2 meters away. So with this, it allows the user to alert the system to try and move away from the wildlife, to be aware that that's happening. And here, this is just feedback to let the user know that the system is aware there's wildlife nearby. Now over here, it's collected some rubbish, so that notifies the user we've collected it. And then it has also distinguished using the capacitive sensor and categorized it as cardboard. So if we know that the rubbish is cardboard, we can choose to send it to bin A, bin B, or bin C.